Hello everybody, myself Prashant Mukhopadhyay, faculty member Electrical Engineering Department, Greater Kolkata College of Engineering and Management. In our last class, we have discussed about the induction machines, particularly three-phase induction, single-phase induction motor, and we have learned there. So in that discussions that how its constructional features, operating how principle of operations, the revolving field theory, cast field theory, different starting methodologies and different single phase starting motors, and also we have learned about the equivalent circuit and how to determine the equivalent circuit parameters, and with that we have completed that chapter. Particularly today we'll start a new unit 5, which is basically of synchronous machines. So basically in this synchronous machines we will learn constructional features, how what are the different types of synchronous machines, how it is being constructed, what are its different parts and components, how the generated EMF, what is the equations of the generated EMF, its equivalent circuit, phasor diagram, armature reactions, synchronous impedance, what is the synchronous impedance, and voltage regulation, operating characteristics of synchronous machines, V-curves, salient pole machines, two reaction theory, and analysis of the phasor diagram, power angle characteristics, parallel operations of alternators, synchronization, and load divisions. So these will be discussed one after another in these discussions, and let us say start with its say introduction. Like all other machines, actually all machines can be operated as a motor as well as generator. So basic difference is with input and what are the output we are actually requiring. Actual thing is synchronous machines also can be operated as a synchronous generator, which is commonly known as alternator, and widely used in today's power generation field. And not only that, synchronous machines also can be used as a synchronous generator. So only basic difference is I told you, that is what is it inputs and what are the what output we are say desiring. So basically same machines, so with the depends of this input and output, so will be can be operated as a generator or motor. So synchronous generator, it is a rotating machine. Actually it's rotated at a speed fixed by its supplied frequency and the number of poles, and that's why and that speed is called the synchronous speed, and that's why the name of this machine is synchronous machine. Basically this machine always rotate in synchronous speed, and this synchronous speed is governed by its supplied frequency and what are the number of poles of this particular machines. So synchronous generator or alternator is an electrical machine that converts mechanical power from a prime mover into an AC electrical power at a particular voltage and frequency. So synchronous machines rotate at a constant speed, and that's why it is called synchronous speed. And the rotating and the stationary parts of electrical machines can be called as say rotor and stator respectively. Here the rotor part is the rotating part, and the stationary part is the stator. And rotor or stator of the electrical machines act as a power producing component and is called as an armature. Basically see the rotating part, whether it may be the rotor or the stator of the electrical machine act as a power producing component of and is called as an armature. The electromagnets or power magnets are mounted on the stator or rotor are used to provide magnetic field of an electrical machine. So basic law is of Principles of operations of the synchronous machine is basically the generator actually the generator which actually in which permanent magnet is used instead of coil to provide excitation field is termed as a permanent magnet synchronous generator, or also simply called as synchronous generator. So basically you know the basic requirement for power generation is magnetic field, and it's a very important field, and within this magnetic field say and a coil rotor or conductor should be rotated to cut the field and to follow the as per electromagnetic law of electromagnetic induction. So EMF will be induced in the rotating part of this conductor. So basic thing is the magnetic field, and that magnetic field can be generated by permanent magnet or by any electromagnet. So the generator in which a permanent magnet is used instead of coil to provide excitation field in terms as is termed as permanent magnet synchronous generator, or also simply called as a synchronous generator. Synchronous generators are usually of three-phase type because of several advantages of three-phase generation, transmission and distribution. So mostly synchronous generators are three-phase type. And large synchronous generators are used to convert bulk mechanical power to an AC electric power at thermal, hydro and nuclear power stations, gas or hydraulic turbine. Okay. Actually so synchronous generators are the primary source of electrical energy we consume today. The biggest size in India has a rating of 500 MVA. So this may be modified later on. There much more improvement may be happened. So this data is not right with me. And for bulk power generation in stator winding of synchronous generators are designed for voltage rating from 6.6 kV to 23 kV. Today up to 33 kV bulk power generations is possible. So in synchronous generator, a DC current is applied to the rotor winding to produce a rotor magnetic field, and the rotor is turned by a prime mover producing a rotating magnetic field. Basically in the rotors, since DC excitation is being provided, so magnetic field will be DC magnetic field will be generated, which is not rotating or alternating. So if by any move any device which is called a prime movers, this magnetic field is being this rotor is being rotated, and this magnetic field will also be rotated. So as a result, rotating magnetic field will be produced. Okay, so and the rotating magnetic field produce three-phase sets of voltage within the stators. Basically, this rotating magnetic field will cut the stationary stator conductors, and EMF will be induced, and as a result, say power will be generated in the stator conductors. So okay. So basic principle of synchronous machine is nothing but it is say transfer or convert electromechanical. It is work as just like electromechanical transducer, which converts mechanical energy into electrical energy and vice versa. In case of generator, it convert mechanical energy to electrical energy, and for motor, it convert electrical energy to mechanical energy. And the fundamental phenomenon or law which makes this conversion possible are law of electromagnetic induction and law of interaction. So basically, law of electromagnetic induction is the first law of Faraday's law of inductions, and this law is related to the production of EMF. That is, EMF is induced in a conductor whenever it cuts across the magnetic field. So that is given as here. This is the magnetic field and this is the conductors. Okay, so whenever this conductor is rotating, so this is the direction of rotation. Basically, it will cut the magnetic field, and as a result, rate of change of magnetic field will happen, and at each and every instant, and that rate of change of say magnetic field will produce an EMF in this conductors, and this EMF will try to oppose the very cause of its generation. That's why E equal to minus n d phi dt. This is the which is this rate of change will oppose its very cause of generations of this EMF. That's why it is E equal to minus n d phi dt. Okay, so this is the basic electromagnetic Faraday's law of electromagnetic induction, and law of interaction means actually this is whenever this law relates to the production of the force or torque, that is whenever a current carrying conductor is placed in a magnetic field by the interaction of the magnetic field produced by the current carrying conductor and the main field, force is exerted in the conductor producing torque. Basically this is a low range force actually. Whenever a current carrying conductor is placed in a magnetic field, force will be generated in this current carrying conductors. So as a result, a torque will be developed. So this is related to whenever a current carrying conductor is placed in a magnetic field by the interaction of the magnetic field produced by the current carrying conductor and the main field, force is exerted on the conductor and producing torque. So basically this is say required for the synchronous motor. So constructional features of three-phase synchronous machines particularly is like this. This is a synchronous generators. Okay, this is the rotors where DC excitation is being provided, and this is the stator, three-phase stator winding. Okay, and so an alternator consists of two main parts, that is stator and rotor. Stator is the stationary part of the machines, and it carries the armature winding in which the voltage is generated, and the output of the machine is taken from the stator. So the rotor is rotating part of the machine and has the field flow. So it produces the main field flux, and the relative motion between the rotor and the stator induces the voltage between the conductor. The manner in which the active parts of the synchronous machines are cooled determines its overall physical size and structure. So basically this is the constructional features actually carries main two things. One is the stator, another is the rotor. Stator is the place where the conductors are three-phase conductors are placed. Okay, this is the stationary part where EMF is being induced or power is being generated, and it carries the armature winding. Basically here say voltage is generated, and the output of the machine is taken from the stator. And the rotor is the rotating part of the machines and has the field fold, and it produces the main field flux, and the relative motion between the rotor and the stator induces the voltage between the conductor. So the manner in which the active parts of a synchronous machine are cooled determines its overall physical size and structure. Okay. Now stator construction. So this is actually the picture shows this stator. Actually this is the slot, armature slot, where the armature conductor has been placed. This stator, this is the stator core. This is stator frame. Actually this is stator frame. So stator core having slots and teeth. In the slots, stator actually this is the slots, and this is the say teeth. Actually this in this slot armature conductor are being placed. So various parts of the stator includes the frame, stator core, stator windings, and cooling arrangement. So frame may be cast iron for small size machines and welded steel type for large size machines. And in order to reduce hysteresis and eddy current losses, the stator core is assembled with high grade silicon steel laminations, and A three-phase winding is put in the slots cut on the inner periphery of the stator, so as that is shown here, and the windings of each phase is distributed over several slots. When current flows in a distributed winding, it produces an essentially sinusoidal EMF. So basically, these are the three windings, three balanced windings, which is being placed in the stator armature slots. Okay. So this is shown here. This is stator. So the main part is stator core, stator slot. So this is stator teeth, and this is the stator frame. And it is, of course, for small size it is of cast iron, and for large size it is welded steel type. And to reduce hysteresis and radical, stator core is assembled with high grade laminate, silicon steel lamination. So silicon steel for say reducing hysteresis loss, and these laminations for eddy current losses. And these three-phase windings, as I told you, put in the slots cut, the inner periphery. These are the inner periphery of the stator, and the winding of each phase is distributed over several slots. And when current flows in the distributed windings, it produces an essentially sinusoidal EMF. Okay. Now we'll discuss rotor construction. Basically, synchronous machines have two types of rotor construction. Mainly salient pole rotor synchronous machines, and cylindrical or round rotor synchronous machines. Okay. So basically, on the basis of the type of rotor used in the synchronous machines, machines is named as either salient pole and rotor, or protrusion pole, or say projected pole type rotor, that is called salient pole rotor synchronous machines, and another is cylindrical or non-salient pole type, cylindrical or round rotor synchronous machines. So these are the two rotors. This is cylindrical rotors. You see here air gap is uniform between the stator and the rotor. This is projected pole. So these are the poles are projected here. So this is actually non-uniform air gap. So here air gap and the quadrature axis is more than direct axis, it is less. So that's why it is called salient pole synchronous machines. So salient pole rotor. So this is an end view of a 6-pole salient pole rotor. Basically, poles are here projected, and see, it is placed in the stator. So, and the air gap, as I told you, is non-uniform. Okay, in the direct axis it is minimum, and quadrature axis, along quadrature axis, it is maximum. So this salient means protruding or projecting. As I told, thus a salient pole rotor consists of poles projecting out from the surface of the rotor core. Actually, this is projected from the surface of the rotor core. So these projecting poles lessen its mechanical strength. This is very important. So its mechanical strength will be less due to these projecting poles. And since the rotor is subjected to changing magnetic fields, it is made of thin steel laminations to reduce eddy current losses. And the salient pole rotor has concentrated winding on the poles. So these are the concentrated winding on the poles. And damper bars, these are the place where the damper bars are being placed. Say damper bars are usually inserted in the pole faces to damp out the rotor oscillation during the sudden change in the load conditions. So this is the pole face where the damper bar, there's a slots where damper bar are being placed. These are the damper bars. Okay, so this is shaft. This is pole shoe. This is actually concentrated pole field winding, and this is the pole body. Okay, So salient pole synchronous machines has non-uniform air gap, that as I told you. So air gap is minimum under the pole centers. So along these pole centers it is minimum, and it's maximum in between the poles. So that's why this is called the pole axis or the direct axis, and this portion, this is called interpolar axis or quadrature axis. Okay. So pole faces are so safe that the radial air gap length increases from pole center to pole tips. Basically, it is formed in this way. So pole radial air gap length increases from pole center to pole tips, so that the flux distribution in the air gap is sinusoidal. Flux distribution is sinusoidal, and this will help the machine to generate sinusoidal EMF. And the individual field poles windings are connected in series to give alternate north and south polarities, and the end of the field windings are connected to a DC source to the buses on the slip rings. So that is actually this is a salient pole rotors construction like this, and the slip rings are metal rings here, actually mounted on the shaft and insulated from it, and they are used to carry current to or from the rotating part of the machine's high carbon buses. And salient pole generators have a large number of poles and operate at a lower speeds. Basically, mechanical due to the projected poles speed is less, and to keep the speed less. Basically number of poles has been increased. So as synchronous speed is 120 A by P, so whenever the number of poles increases, since the supply frequency is constant for a particular supply system, so only the number of poles, if increased, the synchronous speed will be decreased, and that's why the number of poles are say created, and as a result salient pole generators have large number of poles and operate in lower speed. And salient pole generator has comparatively a large diameters to accommodate this large number of poles or diameters of the salient pole synchronous machines will be large, and axial length automatically will be short. So a large number of poles in the rotor makes the rotor larger in diameter and smaller in length, and the large diameter accommodates a large number of poles. And salient poles generators driven by water turbines are called hydro alternators or hydro generators, and this type of rotor construction is used for low speed applications such as hydroelectric generators, etc. So now for cylindrical rotor, so this is a cylindrical rotor type. So this is 2-pole type and this is 4-pole type. End view of the cylindrical rotors or non-salient pole type rotors. So basically rotor conductors or bars are placed in this slot. Okay, and cylindrical rotor machines is also called non-salient pole rotor machines. It has its rotor so constructed that it forms a smooth cylinder, and as a result the construction is such that there are no physical poles to be seen, as in case of salient pole construction. And cylindrical rotors are made of solid forgings of high-grade nickel, chrome, molybdenum steel, and in about 2/3 of the rotor periphery slots are cut in regular intervals and parallel to the shaft, and the DC field windings are accommodated in these slots. The windings is of distributed type, and the unslotted portions of the rotor forms the pole faces. Okay, so that is shown here. This is about the cylindrical pole rotor, and the smooth rotor of the machine makes less winding losses, and the operation is less noisy because of uniform air gap. So the end view of such a 2-pole and 4-pole say machine is rotor is shown here. Okay, I discussed, and say cylindrical rotor machines are driven by steam or gas turbines. Cylindrical rotor synchronous generators are called turbo alternator or turbo generator, and such machines are always have horizontal configurations installation. The machines are built in number of ratings from 10 MVA to 1500 MVA, and cylindrical polar pole rotor has the DC field winding embedded in it, and the cylindrical rotor provides greater mechanical strength and permits more accurate dynamic balancing. So it is particularly used in high-speed turbo generators. So that is about the rotor construction. So as I told you, so now actually most of the cases we find that alternators have the rotating field and stationary armature. So the rotating field type alternator has several advantages over the rotating armature type alternators basically. So what are the advantages? Basically a stationary armature is more easily insulated for high voltage for which the alternator is designed, and this generated voltage may be as high as 33 kV. So if this armature is stationary, so it is more easily can be insulated for this high voltage generation purposes, and the armature winding can be based better mechanically against high electromagnetic forces due to large short circuit currents when the armature windings are in the stator. So this is one of the to get the better mechanical strength to brace the armature winding in a better way. This is windings are placed in the armature windings are placed on the stationary part, and armature windings being stationary are not subjected to vibrations and centrifugal force. As a result, it is high to produce high voltage of the order of 33 kV or like that. So due to this high voltage armature winding, if it is in the stationary conditions, so it will be free from vibration and centrifugal forces, and the output current can be taken from fixed terminals on the stationary armature without using slip-ring brushes, etc. Since armature windings are on the stationary part, so output can be taken out freely, easily without using any slip rings and brushes. And the rotating field is supplied with the direct current, and usually the field to provide to field voltages between 100 to 500 volts. Only 2 slip rings are required to provide direct current for the rotating field, and while at least 3 slip rings are would be required for a rotating armature. So the insulation of the 2 relatively low voltage slip rings from the shaft can be provided easily, whereas if it is generator core is being taken out from the rotating part, so insulation will also be more complicated and costly. And the bulk and weight of the armature windings are substantially greater than the windings of the field poles. So the size of the machine is therefore reduced. So if it is a bulk portion is under rotation, so there is every position possibility of due to great centrifugal force, some damage may happen. So rotating field, since it is comparatively light and can be constructed for high speed rotation, so the armatures of large alternators are forced cooled with circulating gas or liquids, and as a result, since the armature winding is on the outer portions of the machine, so cooling can be made easily, and the stationary armature may be cooled more easily because the armature can be made large to provide a number of cooling ducts. So that actually this say stationary armature and rotating field will provide a great advantage over this rotating field type machine than rotating armature type machine in case of synchronous machines. So in a nutshell, that's about the construction and constructional features of say synchronous machines, particularly in synchronous generators. So we have seen the basic difference of construction of particularly of the rotor of say it may be cylindrical rotor or non-cylindrical rotors or which is used in steam turbine thermal power generation say field where speed is very high. And in case of hydro generators, we are using a salient pole types where the poles are projected and say number of poles to be accommodated is more, and the speed of the synchronous speed is very less in comparison to 2 or 4 pole cylindrical rotor synchronous machines or alternators. So hope this will give say little bit idea about the synchronous machines or alternators, or if we think about the synchronous motors also construction type or same, only difference is the input and what output we are say trying to get out of it. So hope you have understood it. Thank you all for your patience sharing.